Welcome to the LIGO lab at the MIT Kavli Institute. Here, scientists work on both the instrumentation and data science for the Laser Interferometer Gravitational-Wave Observatory. This project involves two enormous and incredibly sensitive detectors that can pick up tiny ripples in space-time produced by the violent collisions of black holes and neutron stars. MIT researchers at the LIGO lab are discovering new cosmic phenomena by listening to the universe like never before.
This is one of the main LIGO labs where we develop technology for gravitational wave detectors. The way we're detecting them is these very large-scale interferometers.
So when the gravitational waves arrive, it stretches and squeezes space as it propagates through the Earth. So what we do is we have a light source, which is a laser, and then we split this laser beam in two parts, and we send it 4 kilometers far, and at the end we have mirrors that reflect the light back. So in some sense, it's very simple. And so what happens is, as the space stretches and squeezes, the light that goes in one arm arrive, let's say, a little bit later than the one coming from the other arm, depending on how the space stretched and squeezed. And so by looking at this delay, essentially, in the light that recombines at this first mirror, that modulation kind of encodes what are the properties of the source that produced the gravitational wave.
Our first big gravitational wave discovery was from a pair of black holes that merged into each other. And so it turned out that those gravitational waves came from black holes that were each 30 times the mass of our sun. And that was the first time that we discovered black holes of that size actually existed. And then we've had many more detections of black hole mergers since then, and we're starting to sort of fill out the picture. What does the population of different sizes of black holes look like across the universe? And that can help with understanding how the universe evolved.
Gravitational waves are special because they do not interact with matter that much. So light, electromagnetic waves, are scattered. Dust can change the pattern when they reach you on Earth, but gravitational waves are unperturbed, and so it allows you to discover phenomena that light doesn't have access to. And the second is, even when you have information about light, for example, when a binary neutron star system explodes, gravitational waves brings you additional information. And so that kind of changed the game of what you can understand about the universe.
We are typically working on what are the improvements that we can bring to the detectors in order to make the detectors much more sensitive, which enables us to do much more science with them in terms of detecting more gravitational waves or different types of gravitational waves. We're opening up this new field of gravitational wave astronomy. Who knows where it's going to lead? Certainly, we're just at the beginning of it.
As we increase the sensitivity, we hope that we can pretty much, first of all, see all of these events. Right now, we just see, some, like a very small number of the events that are out there. And then the other thing is there might be other phenomena that produce gravitational waves and we don't know yet because they're not so easy to detect. But if you can increase the sensitivity of your instrument, a signal that right now is like this and maybe is hidden in the noise, right now will become very big. And so we can detect, let's say, everything else that is out there that we don't know yet.
Up until 6 years ago now, we hadn't detected gravitational waves. We didn't know if black holes exist in binaries. And now we've detected like tens of these types of systems. Like, it's a really new field, and we are literally like discovering new things that humankind has had no access to before, like the early universe. So the cosmic microwave background is the farthest back in time that we can look with light. But with gravitational waves, we can probe back past that, and we can look back to like the moment immediately after the Big Bang. It's just really exciting because we're able to look at new things that we haven't been able to see before and potentially learn like what happened at the very beginning of our universe, which I think is pretty cool.